Welcome to yet another machine learning reading group episode 4. This is another machine learning reading group where we present our own papers. Today we have Tom as our presenter. Neither private nor fair, and the impact of data imbalance on utility and fairness in different privacy, which is super excited for this. Maybe we can do a roundtable of intros for those who just joined for the first time in this episode.
Cool. Yeah. Hi, everyone. I'm Tom. You'll hear more about the Neither Private Nor Fair paper, but I run the product teams at Causal Lens, which is a causal AI, causal inference company. We sell to big enterprises and we help them identify causal relationships within their data. I did this work while working at Selden, which is an MLOps company. So yeah, super excited to be here, and thanks, Maria, for setting it all up.
I'm Oisin. I'm from Ireland. I'm doing a PhD in the Netherlands at the moment in Eindhoven, studying machine learning and signal processing. And yeah, looking forward to your talk, Tom.
Hello, I'm Arjun, and I'm currently working in a neuroscience lab at UCL. Looking forward to the talk.
I'm Carl. I'm a software engineer with a background in machine learning.
I'm Matthew. I'm based at Scale, and Scale does both kind of data for AI model companies, but I also work on custom AI models for enterprises and governments.
Hi, I'm Davide. I am currently studying Master in Data Science and Machine Learning at Imperial. Looking forward to the meeting today.
Cool. All yours, Tom.
Perfect, thank you. I'm going to be presenting about the paper that I published called Neither Private Nor Fair. This was a collaboration with these fine folks. So it was really Fatima and Sahib who I was working with kind of day to day. And then Andrew Trask is the guy who runs the open source community called OpenMind, which is focused on privacy preserving machine learning. During COVID, like everyone else, I found myself with a huge amount of free time, and like nearly no one else, I decided I wanted to dedicate that to publishing machine learning research. So I've always had a bit of a chip on my shoulder about my technical ability, so I wanted to kind of challenge myself and prove that I could do this. This paper was actually accepted into the ACM Computer and Communication Security Conference, which I would say is probably on par with NeurIPS in terms of prestige. No, it's not, but it is a reasonable conference, and the paper itself has 98 citations, which I'm pretty pleased about. I think my kind of main learning from all of this was like, if you are interested in kind of publishing and have no real academic background or experience in the space, joining an open source community is one of the most powerful things that you can do. And OpenMind was a really good place for me to do that. So onwards, I think the first question here is, why should I care? Why did you tune in? Well, I think, there's a lot of interest at the moment around privacy. Apple run adverts on it, so consumers must care. That's how the world works, right? And there are other big tech companies like Uber who have actually released privacy preserving libraries using the same techniques that I'll talk about here. So Uber themselves have an open source library based upon differential privacy that we'll get into in a second. And what that allows people to do is to send SQL queries into an aggregated database and get privacy preserving aggregated calculations back. These are obviously two kind of big tech examples, but hopefully, as you see, there are far deeper implications and far kind of greater societally good things that can come out of this type of technology, particularly in really protected areas such as healthcare. And that was a kind of a key focus of the OpenMind community. A lot of the people came from kind of government and healthcare backgrounds or insurance backgrounds where, personal health information, personal protected information is really, really kind of strongly regulated and constrained. So with that kind of scene setting, also feel free if you've got at any point to jump in with questions, we can keep them running as we go. So I think with that, let's talk a little bit about what differential privacy is, because fundamentally that's kind of the foundation of the paper. So differential privacy is a set of algorithms and way of thinking about privacy that provides a strong privacy guarantee. So the way to think about it is, if you have a function and performed that function on database A, which has your data within it, you're going to get a certain output. That function is differentially private if and only if you can perform that same function on a similar database that is exactly the same, apart from the fact that you've got your row of data changed, and get a similar enough output between them. So it effectively prevents reverse engineering the identity of anyone in the database, even if you know the identities of everybody else within that database. So hopefully that implied that hopefully you've kind of grasped just how strong that guarantee is. If you've got a database of 100 people, you know 99 of them. If that is kind of the output you're looking at is differentially private, then you would never be able to know that final person, even if they were removed from that database. So this is really quite interesting, and this is then kind of been applied. So there's obvious implications for this from kind of interacting directly with a database, but fundamentally, as we know, within this group, you know, a neural network is somewhat, in a supervised machine learning case, certainly somewhat a approximation of a database, right? It's kind of this fuzzy sort of set of weights that kind of approximates this data set and has learned some function about it. And so,
Oh, sorry.
Yeah.
Do you have an example of such a function?
That is differentially private.
Yes.
Yes, I do. I will talk about differentially private stochastic gradient descent now. So thank you. That's a great primer for me, Carl. So if we turn to the machine learning world, what we can see is in typical kind of machine learning settings, we will train on a given amount of data. We then do, you know, batched SGD. We take mini batches of this training data, and then we calculate gradients that are used to update the weights of our neural network during back propagation. We then kind of average those out and actually update the gradient, and that's how we kind of iterate towards a loss function and a performance of our model. So the challenge with this is that if you just use vanilla SGD, there are a number of attacks that you can perform to actually extract training data from these models. We've seen this. I think my favorite example most recently is obviously LLMs. People have been hacking those and performing adversarial attacks on those, but there was a paper that basically that went viral on Twitter where researchers basically just asked, I think it was ChatGPT, to repeat a word endlessly, and eventually it starts spitting out all of this training data that it's been trained on. And so what DPSGD does is it effectively adds two key steps. So it introduces this idea of the moments accountant, which basically keeps a track of the privacy loss over the entire course of training. And what this accountant does is, as you get these per example gradients, you clip them. So if you have an especially strong influence from one given data point, if that's going to update your weights kind of very, very heavily and above a given threshold, then that is then clipped. And so that this prevents the influence of any one single data point. And then when you take your average gradient, you can then add noise to that. And so you can actually, you effectively just add Gaussian noise, and that introduces variation such that, you know, your model, as your model trains, it learns less about the specific instances of your data and more on the aggregate kind of correlations and patterns that you care about during this training process. And so you'll see this come up as we talk about the results, but the clipped gradients are represented by a Z parameter, a threshold Z, and the noise parameter is represented by an epsilon term. Slightly confusingly, the higher the noise parameter, the weaker the privacy guarantees. So if you have a very, very small epsilon, you have very, very strong differential privacy. But if you have a very high epsilon, you have weak privacy guarantees. And if you want to, I can show you the kind of maths behind that if that's of interest. But hopefully, Carl, does that answer your question about how these types of algorithms work?
Yes. Thank you.
Okay. Awesome. So what we set out to do is we set out to understand how actually training using differentially private stochastic gradient descent actually impacted these neural networks. There were some kind of small scale anecdotes of how these how this algorithm would actually hang together in real life, but no one had really kind of shown based on real life utility and fairness metrics, how training with DPSGD would work. Now, because you're adding noise, you would expect that your accuracy to drop, and that's quite intuitive, but no one had actually quantified exactly how that accuracy drop would look, what that would look like. And so we set out with a ResNet. We used the Celeb A dataset, which is just a bunch of celebrity faces, if you're not familiar with that set. And what we did is smile classification. So it's a very, very simple supervised learning task. We took a subset of 30,000 images from Celeb A, 15,000 of them smiling, 15,000 of them non-smiling. But what we did then is varied given subgroups within that data. So we wanted to see how data imbalance and how these privacy guarantees would impact different levels of kind of the utility and the performance of the algorithm on different subgroups within the data. This is important for things like fairness. So if you have a protected attribute that is a minority class within your data, you want to make sure that you're not discriminating against them further, as opposed to looking at the majority class. So we use gender as our example. And then we also looked at a range of different levels of differential privacy. So we varied the amount of noise, we varied that epsilon term, and we also varied the gradient clipping. More specifically, we trained this ResNet for 60 epochs, 32 batch size, like 10 to the -5 learning rate. It's a very standard sort of training. Really, we were looking at how this small tweak, or well, not a small tweak, but this change to the gradient descent algorithm impacted the performance. One of the key advantages of using Celeb A is that as you get stuck, you can always browse through and look at Brad Pitt's smiling face. That cheers you up when you're stuck on bugs. So that was a nice side effect of working on this data set. So what did we actually find? So let me just, so this is actually how training accuracy changed over time. So how our model learnt over the course of the different epochs that we went through. So let me just make sure that we are all clear on all of the different multicolored squiggly lines. So what we did is we trained here on a 70-30 split. So in this case, we have 70% females in the data set and 30% male celebrities. We then trained on different privacy guarantees. So we held the parameter Z constant, but changed the amount of noise that we introduced. So as you can see, low values of epsilon equal high privacy guarantees. And so for each line, we can see the different accuracies. And so we can see here for high levels of differential privacy, as we would expect, you actually get much lower levels of overall accuracy. You can see here training without differential privacy at all. You immediately get, because this is somewhat of a trivial task for a ResNet, you immediately get huge kind of accuracies for just training without differential privacy, but you still get this difference between the female subgroup and the male subgroup. But you can see that as you add differential privacy, interestingly, for the lower levels of differential privacy, that subgroup delta is actually increased. So the level of kind of the minority group here isn't that minor, right? Like there's 30% of the data set is males, but even for very, very low guarantees of differential privacy, there's a 5 and 5.2% disparity in accuracy between the two subgroups. We found that as we increased that imbalance, so as we increased the population of the minority subgroup to 0.1%, we actually saw that this increases, across different stages to 19 and 52% as a subgroup. So you really see, if you are training with differentially private data, you really see a massive loss in accuracy between your subgroups, because this noise, because this gradient clipping means that you're actually washing out those underrepresented groups. I think there's a question. Why more females? Just because it was a balanced data set, and it was basically a coin flip between the two. And we decided that females, you know, are usually in the minority in tech-related questions, so we wanted to flip the scales on that. No real reason. So
Sorry, Tom,
once
I had
you
a quick question on the previous
yeah.
slide. I'm just really curious about how increasing the noise level can actually cause the accuracy to go up. Like maybe you're going to get to that later, but if not, it looks really surprising to me that adding more noise to the gradients makes the performance better in this case.
In terms of
like the low differential privacy case, the epsilon, is that like the standard deviation of the noise you add or something like that? Or
yeah, so this is like this isn't a direct representation of the noise. Like so, like the low differential. This is kind of the counterintuitive part. The low
yeah.
like high epsilon means you actually have less noise, just purely because of the way the maths of the output works.
Okay.
So
Gotcha. So it is actually higher noise.
Exactly. Yeah. So like the epsilon is this, and effectively, if it's differentially private, then this like the piece with the epsilon is less than this. So as you increase your epsilon, you actually want this to be less. So it doesn't correspond directly to the noise itself that the algorithm's adding, but like intuitively, it's the parameter you use to tweak how much noise there is.
Gotcha. Yeah. No, it's the error that you accept kind of on your own.
Exactly.
Thanks.
All right. Okay. So as I mentioned kind of previously, like as you actually start to increase the amount of imbalance, you get higher and higher divergences of accuracy. So you can see here that the green is the most imbalanced group. So you have 99% female here, and that has the largest delta and drop off in accuracy. You can see that like at this stage, the overall accuracy, that solid line, is totally dependent and totally buoyed by the majority group. So if you then look at test time accuracy, you see some interesting things. So I would say if we look at the imbalances that are less than 99.9%, you can see here that obviously our non-differentially private has the lowest delta in accuracy. So this is the accuracy, basically the difference between the test accuracies compared to your male and female subgroups. And you can see here that non-differentially private is actually the best here, as you would expect. But strangely enough, high differentially private for everything but that 99.9% case is really the one that has the least kind of accurate, the smallest accuracy gap. And you can see this represented in some of the previous figures where the high differential privacy, while having overall worse accuracy, the difference between the groups is actually the smallest. So this is kind of counterintuitive. But what we theorized is that due to the noise addition from in training being so high during these differential privacy guarantees, it basically causes all of your gradient and signals to be so similar that learning updates are equal regardless of the subgroup. So you effectively learn kind of signal that's very, very similar regardless of the subgroup. And that means that you actually end up with this delta of accuracy that's smaller for these higher privacy cases, because effectively you're making a neural network that's basically guessing. It's not learning as well as it should, not learning as well as it could. So as and then just the final one, the 99.9% imbalance, you can see that like even non-differentially private kind of the non-DP example here actually trains pretty badly, and you get some big spikes. We then varied the clipping bound. So we started to change the amount of gradient clipping that we actually saw. So and kind of similar thing that we saw, like the clipping and the noise actually obfuscate the gradient signal to such an extent whereby all samples have a similar training effect. This is just showing that as you kind of clip further, it doesn't make as much of a difference. But still, we saw that the smallest difference in subgroup accuracies is found within that high differential privacy example, even though the overall accuracy is lowest. But we didn't see any major impact of actually these gradient clipping, which is why this graph looks pretty boring and pretty horizontal. We also tested fairness metrics. So we were interested in knowing not just utility, but also when you have these these minority subgroups, typically you may have some sort of protected attribute that you care about. And it's likely that the intersection of use cases where you want to apply privacy measures and where you have fairness concerns is quite high, as mentioned, private health information, PII, all that sort of stuff typically falls into this range. So we also looked at two kind of simple fairness measures. So the difference in demographic parity. So demographic parity is effectively satisfied when a model's predictions have the same predicted positive rate across different groups. So a value of 0 means that you have total parity across your subgroups. And as you can see, we kind of saw similar effects for the utility, whereby your non-differentially private stuff is kind of performing the best. But really, there weren't any discernible kind of trends that we could extract, other than, again, as you get to these really high imbalances, everything goes wonky. The second one was, this equality of opportunity, which is another fairness measure, basically requiring that the conditional probability of your classifier is kind of predicting your class is the same given a change in the sensitive variable. So even if the sensitive variable, if the person is male or female, holding everything else equal, your conditional probability of the classifier is the same. And again, as you can expect, your non-differentially private example is actually the most fair, and adding this noise impacts both your utility but also your fairness. And this wasn't something that people had kind of tested before and looked into. Interestingly, this kind of measure appeared that the adding seemed to kind of follow the more intuitive trend that, like, the higher the privacy guarantee, so the more addition of noise meant that your delta was larger, whereas the demographic parity kind of had more of a fuzzier effect. But as we'll talk about at the end, one of the areas that we had kind of future directions is basically we didn't have enough compute to run a huge amount of these trials. So as you'll notice, something that's missing is error bars in these sorts of things. So we didn't manage to kind of run a huge amount of experiments. So future directions that we then looked at, basically adding error bars, confidence intervals, that sort of stuff. So training multiple models to look at these. We did run kind of multiple examples and tests, but we were kind of bootstrapping and scrappy. So GPUs are expensive and I was poor, and that led to not as kind of thorough science as I would have appreciated. And then also looking at kind of different mitigations of this. So there are multiple sort of other privacy preserving methods that we could have kind of gone into. The one that I quite liked the sound of is the private aggregation of teacher ensembles, or PATE, I don't know. That basically you train a set of machine learning models on each of your subclasses, on your sensitive subclasses, use those to generate predictive labels, and then train a student model on those predicted labels. And that kind of pipeline sort of obfuscates a lot of the training examples. So I like that because it sounded pretty cool to be able to set up and do. So yeah, that is basically the presentation. Any final questions or any thoughts?
I had a question. You mentioned earlier that this is something that Apple and Uber were already doing.
So Uber's library was more focused on how you can run like analytical queries against a SQL database. So it wasn't for training neural networks. It was like, okay, I want to know, I don't know, the median spend across Uber customers. Basically, it was a way of running that in a differentially private way. So it's less about like the neural network training side of things. Yeah.
Can you mention like, so let's say I have a model that doesn't use the privacy feature, like what can you tell about the training set?
It depends on the sort of attack that you do on that data. You can basically reverse engineer in a lot of cases, like real examples, very well approximate even like almost the ground truth data from the neural network without any privacy guarantees.
So it's possible to like, if I have a ResNet label to get the actual training image.
Yeah. Yeah. I can dig up some papers that like talk about the examples. I can't remember how they do that off the top of my head, but there are definitely like kind of like adversarial attacks that you can run where you poison the data and it'll kind of like, or you can like based on the labels that you get out, you can reverse engineer the types of training data that it was on.
Okay.
This is crazy.
Yeah.
Any other questions? Well, Tom, you are an excellent presenter. This was really, really well explained. Great graphs, great paper.
Chef's kiss. Thank you.
10 out of 10.
I appreciate everyone taking the time after their busy Mondays.
Ciao.
Thanks, Tom.
Thanks, everyone. Great to meet you all.
Next one.
Bye.
Bye.
Yes.